Okay, good afternoon, everyone. Welcome to the program today. It's my pleasure to introduce today's speaker, Dr. Perello, from University of Manchester from UK. Dr. Perello got his PhD from University of Pittsburgh, and after a few years of stay in Korea as a postdoc and research professor, he moved to UK to join the group of Jim, considered as the father of graphene, won a Nobel Prize in 2010 in physics to work on graphene-related research as a postdoc or research associate. Dr. Perello is also one of the candidates for condensed matter physics faculty position. So today he will talk about ultra-clean graphene devices from ballistic superconducting devices to quantum Hall physics. Please join me to welcome Dr. Perello.
Thank you, Professor. So I've changed my title a little bit. I originally had ultra-clean van der Waals devices, but I realized that I was actually only going to present results on graphene, so that seemed a bit wrong. The two topics I'm going to discuss are pretty disparate, so they're on two sides of 2D physics, but I'll try to bridge them together with a common theme. So outline, well, I don't really have to cover my background now. I'm going to cover a lot on van der Waals materials, a lot of the basics to what we really do in this field, and some of the challenges and some of the really, really big things we can still do with graphene, even though it's 15 years old. So the first major topic will be just on ballistic Josephson junctions and why the fact that they're ballistic matters and what unique physics can happen. Finally, we'll cover hyquids, which are hybrid squids, essentially. And at the end, the second topic, which is dissipation in the quantum Hall state. So, well, you've already got my background. My research history, just so if you have other questions after the colloquium ends, I started with carbon nanotubes, worked with nanowire sensors, did a lot of growth, actually. Did aligned carbon nanotube growth, graphene, single crystal graphene on wafer scales. Then I moved into a lot of, quantum Hall physics, especially when I got to Manchester, but I started it when I was in Korea. And I did a lot of equipment development, UHV, glove box, cluster development, worked on a variety of 2D materials, mostly in exfoliation on these black phosphorus, MOS2, and hafnium sulfide are just three examples. So my current research, of which I'm only going to talk about the black colored topics, works with superconducting devices made from 2D materials, then imaging dissipation and edge effects in the quantum Hall state. But I've also worked significantly, especially recently, on marginally twisted bilayer graphene and the so-called twistronics or engineering flat bands in graphene, as well as some other quite different projects such as hydrodynamic corrections in optimum doped lanthanum strontium cuprate, which is still ongoing, or other twistronics like composite Moire superlattices. So van der Waals materials. Essentially, it's a 2D sheet which is covalently bonded or strongly, just even layman's terms, strongly bonded in plane and weakly interacting out of plane. There's a lot of different examples, some of the research from here. So they have a lot of interesting physical properties, electronic properties, optical properties. It's really a playground for physics. So this is one example with anisotropic excitons in black phosphorus. We have layer-dependent magnetism due to variations in the exchange interaction, depending on how many layers you have and the stackings. You can have superconductivity. I'm sure everybody has heard of this. If you twist two different layers of graphene with specific angles, you get flat bands, and you can induce strong electronic correlations. There's a lot of candidate materials. Right now, the best number I've been able to find is 700. I think that's probably an extremely low count of what the actual number of materials is. So we have a lot of room to play. So one of the things we'd like to do is take these materials and combine them to make either a heterostructure with different properties, or even just be able to isolate a material like graphene and inside a perfect dielectric environment, so with as little Coulomb disorder as possible. So essentially, the reduced degree of freedom, we have a plethora of beautiful physics that results. The problem, however, is that there's a lot of growth quality issues, and I think I'm preaching to the choir for the condensed matter people here, but it's very difficult to grow electronic quality crystals, even whether it's there it goes. Whether we use CVD, CVT, flux growth, or MBE, which can typically grow even single crystal, say 3-5 materials that are maybe a centimeter in quality, it's extremely difficult thus far with van der Waals materials or 2D materials in general. So this is one example where the top are commercially exfoliated tungsten selenide, and the bottom were flux grown. So the scale here is 500 nanometers. So you can see there's still quite a lot of defects. This is tungsten selenide, so we still have a long way to go. So for electronic quality crystals, you can still get it from bulk, but you have to kind of judge where you're getting the material from, and the source matters a lot. And for monolayers, it's really complicated thus far. I don't think we have any perfect electronic growth reports, except for graphene, of course. So to make these designer materials that I showed 2 slides earlier, it's pretty low tech, actually. So what we're doing is we take a microscope and we use a stamping process. So with a PDMS stamp or some type of polymer, where we have a glass slide and we're just picking up material after material. So we use the Scotch tape method, a little more sophisticated than that, but that's the gist of it. And once we exfoliate it onto a material, then we use this to kind of combine the materials. And I say it's a game of adhesion. So you're basically operating these polymers right around their glass transition temperature, and you can lower or raise the temperature to make the adhesion either stronger or weaker between the substrate or between the relative crystals you're trying to pick up. So just a little demonstration, one example. So we would take this glass slide, which is the green here, with a little polymer stamp on the bottom. We would say pick up HBN, which is a great insulator, and graphene, pick that up, raise the temperature, so we pass the glass transition temperature, leave it on the substrate. Now we have essentially a perfect dielectric environment for the graphene, and we can have some fun with physics. So this is one actual transfer that I did a few years ago, actually, and the scale here is about 100 microns. So we're still dealing with small flakes. We don't have wafer scale things. This transfer is, as the diagram showed, it's just putting down the HBN graphene stack onto a bottom HBN, which is the bottom HBN is this large piece, and this is the HBN graphene. So this transfer actually took about 2 hours to do, and this is the result. So what we end up with is a basically perfect interface. So the scale bar on this is not showing, and it's about 2 nanometers from the darkest color to the lightest. So if this is really about as perfect as you can get for combining multiple materials together. There's no polymer between it. There's nothing. And the graphene area is defined by this. So this is about, I think the part that I'm showing is about 80 microns. So we can make very large stacks that are very, very perfect. So I talked about van der Waals materials and mentioned that defect density is still an issue, which is the reason why today I'm actually going to show graphene work. Because if we want to explore especially ballistic physics over many microns, and in some cases up to 50 to 100 microns, mean-free paths, we're stuck with graphene currently. Although there are a few other materials that are looking promising. There's a few issues which we can discuss later. The other issue is that you need a very, very perfect insulator, because if you're measuring graphene, you're measuring everything around it. You're measuring the dielectric environment that it's sitting in. And if you surround it by a perfect insulator, you ideally could then measure graphene itself, which is still a challenge. And the only option we have right now for anything that comes close to the quality of graphene is hexagonal boron nitride. And actually, there's only yes?
I'm sorry, I'm an astronomer. What is a transfer measurement? What are you measuring?
Oh, the previous, that's just the fabrication process.
Oh, okay.
Yeah, so we're taking these flakes, it's very low tech, really it's not scalable at the moment. We would like to be able to grow those materials, but like I said, the defect density is high. So we use a crude method to make very, very beautiful materials. So graphene's 15 years old. Why still care? That's the question that I've heard. I think personally that graphene has 50 more years of research left. If twisted bilayer graphene is anything to the recent, well, a year and a half ago discovery of superconductivity is any indication, we have a lot more to look at, and really we're just getting to the prime years, I think, of this material, as I'll show. So the early devices were just these long hole bars on SiO2, and this famous V curve sitting on SiO2 substrate. The disorder level, or the background charge, is basically determined by the oxide. So the answer was, well, let's suspend the devices, which is wonderful. You can actually get a very, very low residual charge density in the graphene because there's no defects around it, right? It's completely suspended. They're not very useful because suspending a single atomic layer of carbon is not only a nightmare, but it breaks. You're really limited on the amount of physics you can explore. Well, after HBN was rediscovered or discovered in 2011, 2012, well, we've been able to make much larger sizes, and we're limited by the phonon mobilities at room temperature, and as we go to low temperature, then we can look at more fun physics. So the recent work, though, now, and I'm just showing 3 of my recent works, show that there's a lot of physics, especially now that we can make very big devices that are ultra clean. So you can look at magnetophonon resonances that show up in very large devices, which weren't previously possible. I'll be discussing this work later, but you can look at quantum Hall physics that otherwise weren't possible. Or we've observed a 26 micron mean free path based on a scanning squid measurement that I did with some gentlemen in Israel with the related extremely large devices now. So we get really high mobilities. Can we match 2-DEG mobilities? And that's always the question. Okay, we can have mean-free paths that are maybe 100 microns, but the typical response from the two-dimensional electron gas community is, well, how high is your mobility? And no, we can't beat them yet. We might have a chance, though. We haven't measured these devices at low density, so we might have already actually beaten them, but we didn't look for that in those samples. Okay, so I'm going to cover ballistic Josephson junctions now. So for the non-condensed matter people, Josephson junctions are superconductors sandwiching a normal material, which is quite often an insulator traditionally. And we follow the DC Josephson effect, in my case, or AC. But you get the Josephson effect, which is when current flows without a voltage drop. So you have zero resistance state that is induced in this otherwise normal material. And the effect is mediated by Andreev reflection, which I'll keep repeatedly mentioning. So these devices are traditionally very thin insulators, so 1 to 10 nanometers thick, and they look something, on the next slide. So one of the ways that would be able to, if we want to analyze such Josephson junctions, is we would put them in a magnetic field, and the magneto oscillations that show up, so this is flux as a flux quantum, so based on the size, so we have a single flux quantum in the area of the Josephson junction, is you get something, it looks like a Fraunhofer pattern from optics. But if you take one of these Josephson junctions, put it in parallel with another Josephson junction in a ring, well, you get a squid, and then you get a response that looks like this. So the simple idea to take from this is that, this pattern tells us where the current's flowing, and it can also just tell us just simple properties of the material. So these type of Josephson junction or a squid can be a very highly sensitive thermometer, circuit element, so for qubits, the most sensitive magnetometers as far as I've ever seen, and things like single flux quantum logic, or it's a nice playground for looking at physics as well. So one example of this, and this is I think from Professor Wu's group, is you can have planar Josephson junctions. So the basic outline is something like this, where you have a thin insulator, which in this case is Al2O3, and it's wonderful because you can use top-down fabrication, you have scalable growth, you can have extremely large currents. The system is very well known, which is great. So I'm not trying to compete with a thin film junction, but we can actually, if we're using a ballistic material like graphene, so a material with extremely long mean-free paths, then we have a few more valves also that we can tune aside. So one of the things we can do is, this is one of my unpublished data sets. So the x-axis here is the gate voltage. So the gate is the electric field across here. So instead of like in the previous system where we had a superconductor, a normal, and a superconductor on the bottom, here the superconductors are on the sides and the channel is actually a semiconductor. Well, if we change the gate voltages, we can modulate the critical current by an order of magnitude or even more. And also the contacts can be extremely long. And we can look for other physics that are not just associated with superconductivity, such as the quantum Hall effect, make quantum point contacts, and we have a very, very long coherence length. So an example of something that we can play around with this is if we take bilayer graphene and we make a point contact. So if you put side gates, this would be a top view, and you try to confine current, electron flow, the supercurrent through the channel, you can play some fun games. So here, this is the electrical properties. So at 10K, it's not superconducting. At 300 millikelvin, it's superconducting. So now we're going to look at the Fraunhofer patterns, like I mentioned before. So this, I would recommend not looking at this because that'll be a little complicated until after I go through. So this is the effect on the four-terminal resistance measured from the contacts of the device while changing the top gate and the back gate. So changing the electrostatic environment and inducing a displacement field across the device. So this was done at 10K. Now at 300 millikelvin, what we're doing here is we take a gate voltage here, which is a certain displacement field, and we sweep the magnetic field at zero current, zero DC current, so just an AC current. The Fraunhofer pattern looks like this. So at that point, the current is being essentially confined to the central quantum point contact with a little bit of leakage on the outside, which is these resonances in the middle. But if we change the gate voltage so we have very little displacement field, we get kind of a squid-like background pattern with a strong lobe in the middle, which you don't have to take a lot of physics from this, but the idea is that this is telling us where the current is flowing, what's going on in the system. So if we keep modulating the displacement field, we can see it just keeps changing. We're in situ changing where a current can flow, the supercurrent can flow in a system.
Question, how do you
Sure.
know that's the interpretation? Bring back that picture. You say you know where it is. In the top left, what's the D? What's the vertical axis? Yeah.
Right here. Oh, so this is displacement field, and this is magnetic field. So
D is what?
D displacement field. So that would be defined.
So you mean the D of electricity and negativity?
Yeah, exactly.
Okay.
Yeah, defined. I think I defined it on.
That's your applied electric field.
Yeah, across the sample.
Okay, then you mentioned something about spatial resolution. You know where it is. How do you
From these, we can model it. You can take an inverse Fourier transform of the envelope of this function, and it'll actually give you a spatial, roughly. But you have to know something about the system too, for that.
Okay, so you have a theory about where the current flows.
Yeah.
That theory tells you this B dependence, and then so you successfully see the bumps in the B dependence.
Yeah.
Which you then tells you where the current.
Yeah.
Okay.
And in this system, I mean, I had hoped to see some type of quantization or supercurrent quantization, but as it turns out, the electrons just flow through it. So there wasn't a lot of wonderful physics, but.
Okay, so the current's getting spread out more and concentrated more, which is why the Fourier transform.
Exactly.
Wiggle bit.
Yeah. So I've a kind of proposal. So why don't we widen this? We have a ballistic channel, right? So electrons won't scatter in the channel. Let's make it a little bit farther apart. Let's weaken the Josephson coupling between the two superconducting contacts. Let's add some normal contacts to the mix. And let's figure out a way, can we control the superconducting phase from the contacts? Well, it turns out it's actually similar to a previous device that was kind of hot, I think, about 20 years ago, which was an Andreev interferometer. But we have a few more valves again to play with because of the graphene. So this is an example device to control the phase. We include a superconducting loop. The superconducting loop is just floating. Well, it would be grounded by the system, and we're only measuring across normal contacts. So we're controlling the phase by magnetic flux that would be flowing through this loop. So what happens? Well, as I showed in the squid example earlier, we get something that actually looks kind of like a squid, except it's not superconducting, right? Because the resistance here is not zero. We're measuring between normal contacts. However, the effect of these contacts is inducing a oscillatory resistance as a function of the superconducting phase difference across the two contacts. So it's similar to an Andreev interferometer. At this point, we can't say a whole lot more, but the oscillatory supercurrent is basically an additive component to what the normal resistance is. There's a few more details if you want later, but it looks similar to a previous diffusive case. So what's interesting here? Well, if we drop the temperature, so the thallus temperature here is something like 250 millikelvin, and it turns out, surprisingly, that when we cross roughly that temperature, that we start seeing general weirdness. So the x-axis here is exactly the same as the previous. So this is the magnetic field as per quantum flux for the superconducting loop. So we see an oscillation that, again, is sinusoidal, fine, but it flips parity. So we get a 2 pi phase shift, a pi phase shift, as a function of the gate voltage, as a function of charge, which was never really feasible to look at this type of system before. So that was interesting. And I want to bring your attention really to two effects. One is that the oscillations in density here, which is controlled by the back gate, are on the scale of 20 microelectron volts. So this is 5 times 10 to the 8 in terms of residual charge density. And I mean, those that work in the 2D field will know, I mean, that's very far on the extreme side of cleanliness. That would be something that is impressive in itself. But the 20 micron electron volt shifts that occur in here match exactly the thallus temperature. So we're probably, just from this, probably something like a resonant Andreev effect. So what happens in long channels is the Josephson effect, we get an Andreev bound state that forms in the channel. And as we make the channel longer, basically that bound state gets, it's kind of a zone folding, you could say, as an analog for a band structure. It breaks up into a lot of different levels. So what we're seeing is likely something to do with injecting resonant electrons into these levels. Not entirely clear, so look at it a little bit more. So the sharp density of states resonances would actually be about the thallus temperature. So this makes sense. If we have a thermal background energy of the carriers that's less than 20 microelectron volts, then of course we'll start to be able to see this effect, which is exactly what we do. But why would there be a parity shift is the big question. So DC bias dependence, which is the bias dependence across the junction, you would think that as you increase the DC bias, you're going to effectively couple to a different bound state in the channel. And it roughly, hand waving, yeah, it kind of does match. And you can see the scale here. It's roughly about 20 micron electron volts. It does not seem to be consistent among gate voltages, though, which I don't have an explanation for, actually. I would love to be able to tell you something, but so every time a new bound state is occupied, you start seeing either a rise or a drop in the resistivity. Now, why parity flips? So this work that I'm presenting, actually, we didn't publish this yet. We're still ironing out some of the details if it's not clear. The most likely effect is that it's a mesoscopic effect. So Andreev reflection is tied together by pairs of electrons and holes that are bound by time reversal symmetry. So it's a little bit different than like a universal conductance phenomena where you just have phase coherence. So it could be that just changing the density a little bit because of the low density in the channel, that the cyclotron orbits of electrons due to the Lorentz force, that they're changing enough that we're actually seeing it interact with a different defect on the edge, or the paths suddenly retrace differently, and we're able to flip the parity. And the second explanation is if you just scan the literature, you can find kind of, we'll say, random observations of an effect or predicted effect in theory, but it's a little hard to judge in this system. So the conclusion, even though we're not exactly sure what the physics is of this specific thing of interest, there's a lot of very big positives that come from this. So firstly, the charge sensitivity. This system itself, while it's not clear if having a charge interferometer would be useful, it's exceptionally sensitive. So 5 times 10 to the 8 is amazingly sensitive. It's operable at 0 volts, so it should ideally be low power. You can tailor the flux sensitivity. It actually has a large resistance change compared to like the previous Andreev interferometers. And it's flexible in that we can add more normal or superconducting contacts to the mix because the Andreev bound state extends across the entire channel. Currently going to look into, well, what if we add 2, 3, 4 superconducting contacts and try to have them non-locally talk to each other. Sure.
So this new phenomenon, do you have any temperature dependence, or are you already at such low temperatures that you can't?
It only shows up, once it shows up, it's fixed. The magnitude of it does increase as you drop the temperature, but above, I think I can, above 300 millikelvin, it looks like this. But if I step the temperature downward, it just suddenly shows up faintly, and then, it's a gradual increase, so it's not quantum in some sense like that, but it does get stronger at lower temperatures. Which might make, if it's related to a resonant effect plus something else, that would probably make sense. Because if these bound state levels are smaller than KT, then we're not really going to see much effect from that. Okay, so secondly, for the second half of my talk, I want to talk about work we actually recently published. But it's exciting in that we were able to observe novel dissipation mechanisms in the quantum Hall state. So quick background again on just quantum Hall physics. You apply a magnetic field, your continuous density of states breaks up into Landau levels. In some sense, we're following a semi-classical, your cyclotron orbit shrinks, and you eventually develop something like this. So imagine if you have a particle, or just you have a box of electrons. You apply a magnetic field. Eventually, you're going to get edge states that form because of the open cyclotron orbits. Everything in the middle can't go anywhere unless there's defects or something else in the system that might, move it slightly. But they're localized. So that area would go insulating or incompressible, to use different language. The size of these is the magnetic length, which is the size of a cyclotron orbit, followed by that formula. So you get something like this. Eventually, you get an insulating bulk. And if we would view this in a quantum mechanical way, where we can take this a line scan from here, and basically look at the energy versus position, you would get constant energy lines that are shaped like this, where they're flat in the bulk because it's insulating. They're localized states. So you get circulating edge current, where the number of current-carrying edge states is nu. So, and that's the number of energy bands, essentially. And one thing is that these edge modes are what we'll call dissipationless chiral edge states. So basically, they can only travel one direction around the edge of the sample, and dissipationless, they shouldn't scatter, right? They're not producing any heat. And if you would measure the resistance somewhere on this box, you should get 0. It's not superconducting. I want to just, to anybody not familiar, there's no Meissner effect. It's not diamagnet. So we have 3 generally guiding principles, and if we have experts in the field, they might nitpick a little bit how I'm wording these, but I think it's for it's easier to easier to follow. So just going to read them. The quantum Hall plateau, the current flows along ballistic chiral edge channels with no backscattering, no dissipation, except at the contacts. So when they enter and exit the contacts, you can of course have heat generated. So in the plateau regions, which would be this region here, so this is from von Kliching's quantum Hall work where you got the Nobel Prize, you can have dissipation. So at those states, the Fermi level would align with this localized states in the bulk, and you can perhaps get a percolation path across the central, the otherwise insulating or incompressible bulk. So the topological state of the system and the corresponding quantized conductance is robust against local perturbations and determined by the bulk edge correspondence. So what that means in layman's terms is that if we would apply a local electric field, let's say gate one part or have a particle sitting on one part of the system, like on the edge, it's not going to affect the overall. You can still get Rxx equals 0. Those quantum Hall edge channels, physically, they're just going to move around the perturbation. And the bulk edge correspondence means that the topological state, so if we're in a system that has nu equals 6, that means that the bulk and the edge there'll be 6 levels in the bulk, 6 on the edge, in a sense. So if we look at a few more properties before I actually cover the work, this value here, that looks 0, right? I mean, I could believe that. And this is from von Kliching's work. But is it always 0, Rxx? Is that value, is it dissipationless, actually? I mean, I know this is theoretically what it's predicted, but the reality is that no, it actually isn't. If you plot that previous plot, as I'm plotting some of my data from a Hall bar, so we're plotting the longitudinal resistance, pass a current, and basically measure resistance along 2 probes. It should be 0, but if you do it in a logarithmic plot, it never goes to 0. Even if you change the current, you change gate voltages, anything, it's never exactly 0. So in truth, it's usually between, I say 0 and 10 ohms. It's something like milliohms to 10 ohms in good devices. In bad devices, you can more. Well, if we want to analyze this, we first need to understand what are the trivial sources that we can just remove and not have to consider. First is measurement. So depending on how you measure the voltage probes, so in this case, if you're applying current across system here, apply very large magnetic field, so you're firmly in the quantum Hall state. You measure the resistance on this side and compare it to the resistance you measure on that side, you can actually get a difference of 10 ohms. And it all has to do with the Hall voltage. Because if you have a Hall voltage built up across here, and the impedance of your measurement circuit is lower than, let's say, one resistance quantum, which is 25 kilo ohms, then it's fairly reasonable that you can have an error of about 1 out of 1,000, which would be single-digit ohms. The other trivial example would be that if your contacts, so this region right here, if it's not designed properly, whether it's too small or you have some outside electric interference or a particle, say, on 2 of the edges, that's somehow modifying the electrostatics in those areas, you can basically cut off these edge states. So instead of getting something like this, where those edge states flow from the contact out, you end up having an edge state that is just within the contact. And in this case, if you measure the voltage, you'll just be measuring the quantum Hall state of the contact and not the bulk. So those are trivial, and once we can remove those factors, because they can be a problem, is there actually a real breakdown of the quantum Hall effect? Well, yes, of course. If you apply very, very large current densities, and specifically if you're near a plateau transition, you can get a percolating path that will exist across the sample. And as a result, you'll get a rise in Rxx or a voltage that shows up here. So, and that is real dissipation. So it's basically an actual breakdown of the state. So what we want to look at, though, is what if we're looking at a system that has essentially no defects, the charge disorder in the bulk is so low that there really shouldn't be a percolation path. So the bulk disorder in devices like this is somewhere between 2 and 3 times 10 to the 9. So it's a little bit higher than in the previous device that I showed, but that one was actually graphite gated, and this one is not. And the disorder potential is significantly less than the Landau level spacing at any point in the sample. So can we still have this percolation path, or how and I mean, does dissipation actually occur? So to look at this, I collaborated with a group in Israel, and we used we'll call a nanoscale squid on a tip, or a scanning thermometer, basically, and it's a quartz pipette with superconducting metals deposited on the edges with a squid loop on the base of the tip. So the loop diameter can be very small. You can use a lot of superconducting metals for this: aluminum, niobium, lead. Lead typically had the lowest noise level, so that's what we used. And it also, you need a material with a transition temperature that is high enough that we can actually look at physics, beyond. We need to go to the quantum Hall effect, right? So we need to be able to go at least near a Tesla. So basically, scan this equipment across the surface, and you can apply a top gate to this, and also measure if there's any temperature changes in the system. Now, this was not previously possible because in graphene, there's no gating on top. There's no proximity doping. We have just an insulator, and like I said, almost perfect insulator. So dielectrically, we can influence it greatly, but we're influencing it locally. So I want to go back to that. It should be protected against local perturbations. So keep that in your mind. Now, if we take that system and we apply 1 Tesla, so we're firmly in the quantum Hall regime, we pass current between this electrode here, which is actually, on the previous device that I showed, it's a small contact, so we're injecting some degree of hot electrons into the quantum Hall states, and we're measuring the current from this we're passing current from here to here, and in this case, we're not measuring any resistance. All we're doing is taking an image of the temperature. So while this current is passing, and it's only 1 microamp, so there's no breakdown. We're firmly in the kind of equilibrium quantum Hall state. Now, as we change the back gate voltage, which is changing the filling of the edge states, or the number of edge states, the first thing that we see is dissipation. That shouldn't happen, right? I mean, that was one of the hallmarks of this, that there's clearly dissipation in this system. And the second thing is that there's no bulk dissipation. So while the edges are lighting up, and this is all temperature change, it's relative temperature change. So the actual number here, we can't comment on what the actual change is, because it's not calibrated to that degree. So we do not see bulk dissipation in that none of these rings, which are resonant inelastic scattering. So it's an electron hitting a defect at the edge and then scattering inelastically off a phonon there. So it's a resonant process, and it shows up as a ring because when you're scanning near it, the potential perturbation from the tip is bringing that state into resonance at a specific potential. Are the
rings the same size as your resolution?
The minimum size of the ring would be, yeah, but it would also depend if you apply a much larger, like essentially top gate, you would be impacting a much larger area, so you'll get a very large ring. But at the minimum, yeah, we could see 40 nanometers if we look closely enough. Okay, so this strictly gives us temperature data, and it tells us, well, maybe our idea about what's actually going on in the quantum Hall effect, needs a little bit of adjustment. And it also has a very strong dependence on filling factor, if you notice this further. So firstly, at higher filling factors, when the density or the number of levels is greater, we see a behavior where it decays. So we see upstream decay, and then as we get closer to charge neutrality, there's a non-local effect happening here, right? There's no decay of this dissipation.
How do you know the instrument isn't causing this effect? Your measurement might be causing what you measure.
Well, we don't see it.
You're perturbing the system with that.
Oh yeah, exactly. Yeah, and we mean to actually. We have to. Otherwise, you have to get to the right potential. Otherwise, the defect level wouldn't be in resonance. So we're seeing something that's there, but we're we're making it more visible basically by hitting it at a resonance behavior. So if that kind of makes sense.
How do you know?
From measuring a lot on these.
Perturbation smaller than the effect you're seeing?
Well, actually, the perturbation in here, because we're only measuring a temperature change, so there's no, we're not actually looking at the resistance of the actual device. I will show on the next slide actually what's happening there, and that gives more clues actually as to why it's. So if you remember, so now rotating, we're looking at the edge. In the previous slide, the dotted line here matches actually the physical edge of the sample, where in the previous slide where there was the rings that were showing up. Now, if we look at where the resistance is changing as the tip is crossing, they're in two different places. So where we see dissipation from the IV characteristics is not where we're seeing heat generation, actually, which is interesting. So there has to be two distinct mechanisms that are going on here. So I think it'll be. We still weren't sure what was going on. So one of the ideas was, well, let's control the electrostatics at the edge better than just having a blind edge. So what we did was made samples that have plunger gates underneath sections of the graphene, and then so we can control the electric field there much more clearly. So zooming in on one of those plunger gate regions, and all we're doing here is changing the gating in this area. And what we see is first there's the ring structure for changing where we see the phonon scattering, and then we see the resistive change from the scanning gate signal. And they don't match up, except for, well, we see the background, there's a background temperature increase here, but it's not resonance. You can just see it's kind of a broad blob, in a sense, in physics term. And the edges are still lighting up, even when we move the current flow away from the edge. So I want to point out, electron-phonon coupling is extremely weak away from the edge. That's been observed in 2 DEGs, and we see it if we're not in the quantum Hall regime. There's no scattering in the bulk. So what's happening here? Well, we have 2 pathways. So if we look at the scanning gate signal, and this is the area that I showed before, and then we compare it to the thermal signal, we see that, well, first of all, there's heat on the edge, but there's also this kind of rounded ring that shows up about 200 or 300 nanometers inside. So there's 2 mechanisms that we propose that have to occur in order to explain this. So firstly, the inner change in resistance is an electron-electron interaction effect, where we have to have some type of backscattering that's where these electrons can't produce heat locally, but what they can do is they can produce heat non-locally. So if they backscatter, let's say at a point right here, then the electron will travel ballistically somewhere else, interact with the edge with inelastic phonon scattering, and then it'll generate a thermal change in the system, because we're observing changes that are extremely small in this in the scaling here. The other mechanism is simply the resonant inelastic phonon scattering. So the thing that this requires, though, however, is quantum Hall edge states are chiral. So we need a counterpropagating edge mode to exist in order for this to happen, and that's a bit odd in that we didn't really expect this in graphene. You see it in 2 DEGs sometimes, which the previous constant energy diagram that I showed before, where it was just kind of rounded, and then the bulk of a device would have a flat spectrum. We see a little dip, which is some type of edge field or edge doping. And as I said before, like, this type of perturbation shouldn't affect the quantum Hall effect. We shouldn't get dissipation from this. But we do when it's not just local, if it's actually a global property to the system that we just didn't think was there. Well, the source of the edge potential, the first easy explanation would be, well, think of a capacitor. If you're near the edge, you have flux lines that kind of crowd at the edges. You can get a little bit of extra density, and that could explain it, right? Well, if we're changing the plunger gates in our system, we don't see a symmetric effect with respect to gate voltage. Because in this case, if you flip the polarity, the effect should be symmetric, right? I mean, you're just flipping which charge it is. It's not. So what it tells us is that every graphene edge is essentially doped. And the fun thing is that it's actually not dependent on whether you etch or not etch, because one of the edges in the previous device that I showed, and I didn't even have to point it out, was not etched. It was just an exfoliated edge, which should be clean. So it's never seen polymers, it's never seen anything. So it's interesting. And as it turns out, in another work of mine, with another collaboration with a different group, we're able to see still a similar 10 to the 10 per centimeter squared edge doping. So it does make sense. It's consistent across samples. So the conclusion in this is, I didn't go too far over, we have a presence of non-chiral or non-topological states. So they're not, when I say non-topological, these states still could be ballistic, but they're not protected by the bulk edge correspondence. So they're not representative of the quantum Hall state. Topological protection is not broken here. We are kind of undermining it in that we can get resistance state that's not reflective of what the actual quantum Hall state of the system is. And the key factor here, though, is that the presence of this edge doping, which is ubiquitous and would extend far beyond just quantum Hall physics, would deal with anything from photocurrent, edge superconductivity, where I was explaining where the current flows in the previous devices, and actually the edge current that shows up in the quantum point contact that I showed a few data sets, very likely is from this effect, and it's really hard to remove, although there are some tricks which I can discuss later. And things like thermal transport, maybe edge reactivity, anybody that makes nanoribbons, the list goes on. If you have an edge field that is not expected to be there, it really can impact, because it could be a PN junction or a PP plus junction. Okay, so acknowledgements, my current advisor, Andreev, these are some other people that either helped with some of the measurements or with various fabrication or details. I worked with the Weissman Institute and Ellie, as well as Ahmet and Arthur on the scanning squid measurements. And any of the superconducting measurements I did at Lancaster with the help of John and Michael. And work was done so mostly at University of Manchester with Horizon 2020. And especially special thank you for inviting me out here. Hopefully I could show you something interesting and I wasn't too boring. And if you were interested, these are some of the papers that were either mentioned in there or that from the last 3 years. So thank you.
Thank you for the nice talk. And now it's time for questions. Okay.
Hey.
Could I ask you to tell me, I'm an astronomer too, and I don't actually know what a ballistic quantum interference device is used for. So what do we do with that kind of device? I don't know how to get understand.
So right now there are no ballistic quantum interference devices. Actually, this would be this or anybody making one out of, say, graphene or another, I think indium arsenide, maybe an indium arsenide nanowire, perhaps, would be the only ones. No commercial application. The applications, though, or the use of it would be the same as a planar Josephson junction, but the difference would be, again, that we can manipulate the control, like we can manipulate how the carriers move in the channel.
I didn't actually really know what the applications are of a planar Josephson junction.
Okay. Thermometer. So basically, actually, the instrument that we used in the quantum Hall measurements, that's actually a squid. So that it's able to measure very, very, very small temperature changes. You can measure magnetometers, I believe, are mostly squids. A lot of them are squids. At least some very, very. You can also use that system that I used there as a sensor for magnetic field, but it's complicated in that the thermal signal actually overrides the magnetic field signal. Because if we're doing it in a, let's say, low vacuum, like it's in helium, the helium ions are bouncing off the tip, so they're transferring heat from the substrate to the. That's actually where the interaction comes from here, but it's reading the heat change. And quantum computing, I guess that would be the big possible outcome of this. So a ballistic Josephson junction, like I mentioned, you can tune the critical currents, so you can change the Josephson energy and you might be able to remove some of the flux bias lines, things like that. Make things a little less complicated, a little bit, maybe. Yeah, hi.
What's your take on quantum computing?
I'm hoping to move into that area. So I would like to use some of these graphene technologies, that I developed and took part in Manchester to make tunable Josephson junctions that could be put in squids. So I think it's a promising way to go. I mean, but I'm in the field, so maybe I'm blind to the. But yeah.
So when you make the device, do you know on the flake the edge is zigzag or armchair?
No.
Or it doesn't matter?
No, there's as far as I know, you can do Raman spectroscopy and figure out an idea. I usually don't do that because sometimes it's more practical just to make two more samples in the same time that you would do another characterization.
But do you
here I don't know.
expect any difference? Do you expect that? Because you're looking at the state.
Yeah.
Can that be a parameter that will change that?
So if it's zigzag, you might have that basically, right? If it's armchair, it might have a short answer. I'm not sure. I think it would be unrelated because I don't think the edges are perfect anyway. Even if they're all along an armchair direction, I think that it would just be locally armchair. And it may change within 30 or 40 nanometers, which is our resolution. Maybe. That might be something to explore, though.
Any other questions?
You mentioned in the center of your device you don't have electron-photon coupling, but you have at the edge. So why is that different?
Probably just defects at the edge. There's no defects in the bulk. And you can see those resonant rings if you pick you get unlucky and you have something in the bulk, or if you make a physical defect in the bulk, you can actually see it at zero magnetic field. So if I go back to here, you can see for a very brief moment in one or two of these squares when we hit a transition between Landau levels, you can see a little bit, I think, in the center. Or maybe not. I think if you look really closely, I think you can see, but it's.
In the rings?
Yeah. But if you do a measurement on devices where there's no magnetic field, you also see nothing in the bulk. So, and we can't do it at room temperature, though, so I couldn't answer that one because this is squid. So.
Okay. Any other questions? If not, let's start our speaker again.